Okay, guys, let's continue with the next chapter. We'll now consider model selection criteria, and so according to that, how would you select an appropriate model from empirical data? Okay, so this is what you would basically do. Okay, so this is model selection, and now from the empirical perspective, not from the theoretical one. Let's say we should estimate, for instance, an autoregressive process, but you're not sure what kind of order should it have. Okay, so then it's basically how would you do this? Now there are basically two approaches here. The first one is the general to specific approach. Okay, so general to specific. Okay. And the other is basically bottom to top, okay? And according to this, okay? So basically, I mean, this is quite obvious. So from the general to the specific approach, what you do is you use a relatively large model first, okay? And then you throw out, the variables which are not significant. Okay, that's basically it. Okay, so insignificant variables are omitted from a relatively large model. Okay, that's the. Okay, so insignificant variables are omitted. Okay? And then we start with the relatively large model first, okay? And the bottom to top approach is basically the opposite, okay? So then you start with the relatively small model first, and then additional explanatory variables are then included, okay? Until really residuals stop being autocorrelated. So additional explanatory variables are included, okay, until for instance, the residuals stop being autocorrelated, okay, so until there is no correlation, is no autocorrelation. Of the residuals. Okay. Basically, you can do both. There are some criteria, so which will help you quantify them. Okay, so the first one is basically the so-called Akaike information criteria. Okay. So this is the Akaike information criteria. Okay, or Criterion, sorry. And this is something that you can quantify here. So what you do is you calculate something here. And this is called AIC, sorry. Okay, so basically this is just the name of it. And it depends on a certain constant here. Okay, so basically this is K. And K is the number of estimated parameters. Okay, so K is the number of estimated parameters. Now there is a trade-off between for K being large and being small. I mean, of course, the larger K is, the higher the explanatory power of the regression would be. Okay, so on the one hand, it's basically a good idea to include several explanatory or additional maybe explanatory variables. But on the other hand, you lose, quite significantly amount of observations, especially the degrees of freedom will decrease drastically, in particular if you have an autoregressive model that you should estimate. Okay, so there are two sides of the coin, let's say. Okay, so here you have on the first side you have 2 times k. Okay, so basically the higher, the larger k gets, the better. Okay, and minus then you have the 2 times the likelihood function. Okay, so this is going to be the log likelihood function. All right, so then basically this is the L is the value of the likelihood function. Okay, so you estimate the likelihood function of the model. You don't estimate it, but you calculate it basically. So based on the given model, what you need to have is, of course, you need to have a specific. If it's an autoregressive process, you need to have an assumption regarding the distribution of the noise. Okay, so then you generate the likelihood function as well. Okay, now you can collect this for several models, and what you do is, okay, so let's say k hat denotes the amount of estimated parameters that you choose for the model, and you do this by doing the following. Okay, so then you would calculate the minimum of this criterion. Okay, that's quite obvious. Okay, so you calculate the minimum with respect to k. So for different k's, okay, you calculate this expression, and if you're done with, let's say, several models, then you would take the one for which basically the center information criteria is the smallest. Okay, so this basically, this is the k hat is the selected. Okay, so this is the selected number of parameters. So that you basically select. So this is how it's done. Okay. So this is the Akaike information criterion, and you have also on the other hand you have the Schwarz criterion. Okay. So this is the Schwarz criterion. This is the other. Okay. Okay. So there are several types basically. Okay. And I call this SIC, okay, for the Schwarz information criterion, okay, depending on basically the number of estimated parameters. And this is just k times ln of t, okay, minus 2 times ln of the likelihood function, okay. So basically here you have k of k is, of course, basically the number of estimated parameters, but here capital T is basically the number of residuals. Okay, so number of residuals. Now you have seen this last week also and last time as well. So if you had, say, for instance, you estimate an autoregressive process and then you increase the number of explanatory variables, meaning that you have a high order autoregressive process, then the number of residuals will decrease. In the first example, we had 6 observations of the time series, okay? But, we were estimating a first order autoregressive process, so that basically means that there are just 5 residuals, let's say. Okay, so as the number of explanatory variables increase, the number of residuals decrease when estimating autoregressive process dramatically. And as for the second order, if the process has 6 observations, right, or the time series, let's say, and you would estimate the second order autoregressive process, then you would basically have just 4 residuals. Okay, so that's basically on the contrary. Now, of course, so you do the same thing. Okay, so for selecting the model, okay, so what you do is, of course, you would calculate basically the minimum, okay? First, okay? So of all models that you consider regarding criteria, and then basically you would select the one for which this expression is the smallest, okay? You understand the argmin notation here? Is that something that you're familiar with, the argmin? No, not really, okay? Let me just give you an example what I mean by this, okay? So this is just an example. This is does not relate to the information criteria. Okay, so what we have, let's say for instance, you have the parabola, okay, plus 1, and of course the minimum, okay, so this is how the function looks. Here in this case, okay, so here you have it, this is the function. Here you have the minimum of the function, right? Okay, so and of course the minimum of the function is basically, I mean, I'll use this as a set here. So the minimum of the function is of course equal to 1, right? So that's the minimum here. There you have it, right? So that's equal to 1. Alright? But this is not the value that you should put into the function to get the minimum. So the argmin, okay? So meaning that the argument that minimizes the function. Okay, so the argument that minimizes the function is basically 0. Okay? So because you have to put 0 into the function to get the minimum of the function. So this is the argument that minimizes the function. Okay? Now here you do the same thing basically. Okay? So because this is a function, okay, here you have the case, the number of estimated parameters so that you might include in there. Okay? And you take the corresponding, or you select the number in such a way that the function is minimized. Okay, so that will be the argument that minimizes the corresponding criteria. Okay, either you take, the Akaike or the Schwarz criterion. Okay, now here in this case you will see that the penalty, okay, for larger models is basically higher. Okay, so in this case, okay, so comparing to that one. Okay, so you have k times ln of t minus 2 times ln of the logarithm. So basically this means that here for the Schwarz criterion, okay, penalizes higher order models, let's say. Okay, so it penalizes more. So then this means that the Schwarz criterion tends to result in, let's say, smaller models. Okay, so the model is not that large as that of the criteria, the Akaike information criterion. Okay, so basically the Akaike information criterion estimate the largest models. Okay, so that's why it's also always considered. I mean, you can look at the information criterion in. I mean, these are just the two. Okay, but the Akaike tends to estimate the largest model, and the Schwarz criterion tends to estimate the smallest model. So that's why they are the most important ones, and then maybe you choose something between. Okay, so in practice, okay, so the Akaike, okay, so information criterion tends to estimate, okay, the largest models, okay, or tends to select, basically, that would be better, anyway. So tends to estimate the largest model, okay, in practice, okay, and the Schwarz information criteria tends to estimate the smallest models in most cases, okay, and the Schwarz information criteria tends to estimate the smallest one. Okay? So that's why they're basically most, these are the most common ones in practice. Okay, so they compute in both cases, you know, the Akaike information criterion and both the Schwarz information criterion, and if the gap tends to be too large, then maybe we would look at another one. Okay, there are several ones which are already implemented in certain programs. Let's say, for instance, EQs. I think there are 10 or something. Okay, so you can display all of them basically, and it's, I mean, it's up to you. Okay, so how you choose the models in particular. Okay, now that was it basically, which was about chapter 5. Okay, I would like to skip the exercises that we didn't consider. Okay, because I would like to have displayed here, but I don't. So I will come back to it basically when we're reviewing that chapter. Okay, I mean, we have the first one, we have the second one, we have the third one, but and the fourth one as well. But if you look at exercise 5.5 and 5.6, there are large tables that I cannot display here right now. So I will do this next time. Okay, I will come back to it next time. Basically, you have to tell whether or not the model is significant, or basically is the model free of autocorrelation, blah blah blah, stuff like that. Okay, so all you do is basically you test the parameters for significance, or you test the model for significance, or you test the autocorrelation for significance. Okay, so that's basically what you would do, and what we can skip that, of course. Okay, so I don't have the distributions table here. I don't have the let's say PDF version of the file here on this computer. So I will skip that exercise, but I will come back to it next week if you don't mind. Okay, maybe you could check it for yourself. Okay, so let's see. I mean, these are the only ones that are missing. Okay, so example 5.5 and 5.6. Maybe I would like to ask you to review it, and then we will look at this together. Okay? Good. Now, these are easy ones, and that are also typical ones for the examination. Okay, so you will likely to get an output, and basically some estimates or not displayed as you see in this exercise, and then you would have to calculate them or whatever, and you would have to perform a corresponding test. Okay, so these are examples 5.5 and 5.6 are also typical for the exam. Okay, now let's continue with the next chapter, and this is also a very important chapter. This is chapter number 6, and it's about conditional heteroskedasticity. Okay, so these are the arch and gorge models. Okay, so conditional heteroskedasticity. Okay, in particular, the arch and the gorge models. This is also, let's say, important, okay, for you, especially for the seminar paper. Okay, so these are models that you can choose from. Then you can estimate, and then you can examine whether or not. So let's say, for instance, there is a conditional heteroskedasticity. What I will tell you what it is. Okay. Now, basically, what is conditional heteroskedasticity means? That basically means that the conditional variance can be time dependent. Okay, so it means that, okay, so conditional heteroskedasticity means that the conditional variance is time dependent. Okay, this is what it means. Okay, so conditional variance, and the conditional variance is basically the variance of the process given its past. Okay, we were looking at the conditional values. So conditional variance given its past, okay, so the past basically of the process can be time dependent. Okay. Okay. It doesn't necessarily have to be, but it can be. All right. Now there is still a possibility for such a process to be stationary, as you will see, okay? So this is not a contradiction here. And this is, okay? This is something that it is possible, okay? So note that the process can be still stationary, because there might be that the unconditional variance does not depend on time, okay? So although, let's say, the conditional variance of the process depends on time, it can be that, for instance, that the unconditional variance does not, okay, still. Okay, and this is not a contradiction, so that basically means that the process can be stationary, okay? I will add this here, okay, so that note that, let's say, a corresponding process, okay, I'm going to call this Y, can be stationary. Again, there is a possibility, I mean, although let's say the variance, okay, or the conditional variance does depend on time, it doesn't necessarily mean that the unconditional variance does not. And we were defining stationarity in terms of, you know, that the moments were not depending on time, especially the expectation, the variance, and the autocorrelation, okay? But please note that this is not necessarily true for the conditional variance. Okay, so that's basically a simplification. Okay, now let me just, okay, so let me just define, okay, a stochastic process for which the variance is stochastic. Okay, so this is just an example. Okay, so this is let me just demonstrate this. So Y is a stochastic process. Okay. With, okay, a stochastic variance, okay. So basically, it means that the variance of the process itself will be stochastic, okay. And I'm going to define this process as follows, okay. So here you have, okay, so Yt is basically, or will be equal to, and then here you have the noise, epsilon t. Now this time, the noise, this is a standard normal white noise. So here in this case, you basically have that the variance is equal to 1. Okay, so this is, or let's say, epsilon here in this case is a independently, I mean, is a white noise. Okay, so but, okay, white noise, where basically you have that the corresponding values here are independently and identically distributed, okay, where the mean is equal to 0 and the variance this time is equal to 1. Okay, I will continue here. So the mean of the process, okay, so this is an IID process, okay, the mean of the process is equal to 0 and the variance is going to be equal to 1 this time. Okay, in the previous setup we had sigma squared for the variance of the noise. Okay, in all models by assumption, by assumption. Now, but this time, what we do is basically we'll add here another process, and I call this sigma. Okay, so if you multiply this by sigma, then you would basically get that this process would be a white noise with the variance sigma squared. Okay, but here basically we have that the variance is time dependent. Okay, so the variance is time dependent. So basically it means that it's also stochastic in a certain way. Okay, it's not narrowly specified here. Okay, so how does dependency look like? Okay, so but it can be time dependent. So if let's say if basically, okay, so if basically let's say that the variance or the volatility of the process depends on time, then the process would not be stationary here in general. Okay, all right, but we're gonna focus on basically on the conditional variance as well. Okay, I mean depending on how this process will look like. So here you have sigma t, which is the stochastic process itself. Okay. Now, what we allow here is that you know, that the variance, okay, so I will take the square of this, okay, so this is the stochastic variance, okay, and okay, is, okay, and this is what we have, okay, so this can depend, okay, this can depend on the past of basically of the noise, okay, so this can depend on the past of the noise, not the current value, but the past, okay. On the other hand, all right, so basically the noise does not depend, okay, does not depend on the stochastic variance, okay, and nor does its past, okay, and it does not depend on the stochastic variance, and it doesn't depend on its past either, okay. So here you have that this, okay, so the noise itself does not depend on neither on the current value of the process nor on its past, okay, regarding the stochastic variance. But on the other hand, the variance, or the variance process, let's say, can depend on the past of the noise. That is allowed, okay? And of course, and basically you would have that, you know, epsilon t and sigma squared t, okay, are independent. So currently, okay, the two are independent, okay, so epsilon and the variance process, okay, so the current value of the noise and the current value of the stochastic variance, they are independent by definition, okay. But on the other hand, the variance can depend on the past of the noise, okay, but does not depend on the current value. All right, so that's basically how it is, okay. Now I'm going to summarize a certain property that this process has, okay. So that basically, I will summarize this, and we'll have a following remark. So let's basically consider that we have such a process, okay. So with this properties, okay. So again, epsilon is a noise, and sigma t is a stochastic variance, basically, okay, or the stochastic volatility, in short. And okay, so the properties are as such as we discussed right now, okay. And then we have the following, basically, and this is what we get. So here, for instance, the expectation or the conditioned expectation of the process, okay, given its past, all right, is going to be 0. Okay. Now this is very easy to demonstrate in particular. Also the unconditional expectation of the process is also 0, and that is because the noise has the expectation 0. And since they are independent, then basically the unconditional expectation is also 0. Okay? And so that's the first property. And that the second property is that basically that the variance of the process, okay, so the variance, okay, is equal to the expectation of the square of the process sigma. Okay, so the variance is equal to the square of this process that we were looking at. And note that basically this does not necessarily depend on time. Okay, so the variance here of the process does not necessarily depend on time. Okay, so the process can be stationary, although basically the unconditional or the conditional variance will be depending on time. So this will be the case. Okay, and if that is true, then basically we have, on the other hand, so this implies on the other hand that the unconditional expectation of the process is going to be 0. Okay, and the autocovariance is going to be also 0 as well. so the autocovariance is also 0 if, let's say, the time lag is greater than 0. Okay? Okay? So there is no serial correlation here. Okay? So no serial correlation of the process, but you have to be careful. It doesn't necessarily mean that there is no serial independency. Okay? So just because there is no serial correlation, it doesn't necessarily mean, especially in practice, that there is no serial dependency. Okay? So basically what you also have is that this process here, okay, is a martingale difference sequence. Remember this? Okay? So basically this is a process that you also have here. Okay, so yt or y is a martingale difference sequence. Again, this will be also considered in the exercises. Okay? So basically the expectation of the absolute expectation of the process is finite. That's the first one. And the second one is that the conditional expectation of the process is 0. These are the properties. Okay, so that's the first property, and the other one is basically ensured by a certain restriction that the absolute expectation of the process is finite. Okay, basically assuming that this is finite. Okay. Now, okay, so with a finite variance, so this is going to be the case. Now, okay, so that's why we start, and now we're going to define an autoregressive conditional heteroskedasticity. Okay, so that's the introduction. So this is going to be part of the next chapter. So what is an autoregressive conditional heteroskedasticity process? Okay, so what does it say? Okay, or what is it? And let me just define this first. Okay, so this is a definition. Okay, so basically y is said to be, okay, you got a question, guys? Yeah.
Okay.
So I just wanted to read those.
Martingale difference sequence, sorry. Okay, so that was a specific type of stochastic process which has a conditional expectation being equal to 0, and the expectation of the absolute expectation of the process is finite. These are basically the two properties. And the first condition basically can be ensured by a certain restriction of the process. So this is, let's say, I mean, if the process is of this type, okay, then basically it's a martingale difference sequence. Okay, so this is a martingale difference sequence. Okay, so we'll talk about this process. Okay. Now, the next one is, or this will be about the autoregressive conditional heteroskedasticity. Okay, so this is why it's said to be, okay, autoregressive conditional heteroskedasticity process, or heteroskedastic. Okay, so why is said to be a autoregressive conditional heteroskedastic, okay, heteroskedastic process, okay. Okay, so this will be the so-called arch process, okay, autoregressive conditional heteroskedastic process, okay, and let's say of order Q. So there are different types regarding the autocovariance, okay? And the notation is, of course, okay, so here we say basically that Y is an arch process, okay, autoregressive conditional heteroskedasticity, okay, and we have of order Q, okay, so that's how it's denoted, okay? If it can be written as follows, okay, so it can be written Okay, so if basically the representation of the process allows us to be as follows. Okay? So first off, I mean, the process itself, okay, it looks like the previous one. Okay, so you have sigma t times epsilon t, and here in particular the variance, okay, so the variance process, or the stochastic variance, or volatility, is also specified. Okay, so I add this here to this definition. So basically, you have that epsilon is a white noise. Okay, so it's an IID white noise. Okay, with mean 0 and variance 1. Okay, and basically, and sigma square is a stochastic process. Okay, is a stochastic process. Okay, and that satisfies basically the following representation. So basically, you have that so the stochastic process representing basically the variance. Okay, so the evolution of the variance of the process can be written as follows. Okay, so I'm using different coefficients. So here you have basically alpha 0, and then you have alpha 1. Okay, times, and then look, this is not the first leg process here. Okay, so you have the square of that. Okay, so basically it depends on the square, okay, of the path of the process. So here you basically can see that if you take the square of that, okay, then you would have that the process, okay, so the variance depends on the path of the noise. Okay, so if you take that, if you take the square of this, basically, okay, at time t minus 1, then you will see that basically that the process depends on the path of the noise. Okay, so this is of order q. All right, so this is not the first order process. This is of order q. All right, so it doesn't stop there, and you would continue. Okay, so here you have, and let me just add this here, the last one. Okay, so you have alpha 1 times yt minus 1 squared, then plus alpha 2 times yt minus 2 squared, etc., etc. And the final one is alpha q times yt minus q squared. Okay, so this is how it's basically how it looks like. Okay, and on the other hand, you have to have in particular that alpha is greater than 0. Okay, so alpha is greater than 0, and the coefficients, okay, are either, okay, so these alpha, let's call them alpha j. Okay, so these alpha j's, the remaining ones, are either greater or equal to 0. So these coefficients here can be 0. Okay, I'm talking about these here. Okay, so alpha 1, alpha 2, and alpha q. Okay, but the first one cannot. Okay, so the first one has to be greater than 0. Okay, let me just complete this definition. Okay, for j from 1 to k, so for all time legs. Okay, now I'm going to discuss certain properties of the process, but this is just, first this is the definition, and I will also explain what this has to do with conditional heteroscedasticity and stuff like that. Okay, so what are basically the properties of the process. Okay, now we can say immediately, okay, that the properties of the process here are listed basically here. Okay, so that's, let me just summarize this. Okay, so this is important here. Okay, so these will be the first properties. Okay, so let me just summarize them. Okay, so let's say if y is an autoregressive conditional heteroskedastic process of order q, then this implies, okay, immediately that its conditional expectation is 0. Okay, so you have to have that the conditional expectation of the process is 0. Here in this case, I mean, this is relatively easy to show, that also the unconditional expectation is also 0. Okay, so this is true for all autoregressive conditional heteroscedastic processes. Okay, and the process is free of serial correlation, so the covariance, okay, or the autocovariances of the process are also 0. Okay, so here for all h greater than 0. Okay, and the fourth property is, and as we see this here before, is that basically that the variance of the process, okay, is going to be equal to the expectation of the squared of the stochastic process here, sigma squared. Okay, so this is going to be the expectation of sigma squared, let's say, okay, which represents a stochastic variance here.
That's bigger than 1? The last one?
Yes. I mean, it depends on the variance here. Okay, so this expression. I mean, let me just illustrate this, because of course, I mean, you have basically you have the variance of yt, okay, which is basically the expectation of the square minus the square of the expectation. So here this is the expectation of the square minus the square of the expectation. Okay. Now, of course, the expectation is 0. So here you have basically this is going to be the expectation of the square of this process, and this is going to be sigma squared times the square of the white noise. Okay. All right. So because that's equal to 0. Now, since they're independent, the expectation of the product is equal to the product of the expectations. Okay. So they are independent. Okay. So this is the expectation of the first one times the expectation here of the second one, and since this is equal to 1 by definition, right? Because the variance of the process is equal to 1. So if the variance of the process is equal to 1 and the mean is equal to 0, then the expectation of the square of the process is equal to 1, of course, right? Okay? So this is what you would obtain. Okay? Now, it depends basically if it's greater than 1 or not. Okay? I mean, it's, you know, depending on the dimension of the process, but it's definitely greater than 0, let's say. Okay? Right, so that has to be the case. Okay? Basically, and this is in short, okay, so in such a way that this is, in that case, this is greater than 0, is ensured basically that by these conditions, okay? So alpha, okay? Because you can look at the process here. Alpha 0, right? So in this case, this condition ensures that the process is, let's say, greater than 0 almost surely. So then if the process is greater than 0 almost surely, then basically then you would also have that the variance of the expectation of the process is also greater than 0. Okay? So I mean these are conditions that ensure, okay, so I will add this here, that sigma squared is always greater than 0, almost surely. So this means that with probability 1, okay? So almost surely, meaning that with probability 1. Okay, so then of course the expectation of that will be also greater than 0. Okay, without any doubt. Okay. Now let me just summarize. So I mean these are properties that automatically follows of the, basically of the definition. So this is what you would generally have, okay, basically. But there are other ones, okay. So what we see here first is that the variance of the current innovation, okay. So this is the variance here, okay. So this is the variance of the current innovation, this one, okay. It depends basically, okay, is a function of the squares of its previous innovations. Okay, so the variance, okay, so let me just summarize also some other properties. Okay, for large okay, so this is what you would have. Okay, so for autoregressive conditional heteroscedasticity, we have that basically the variance of the current innovation. Okay, so the variance of the current innovation. Okay. And I'm talking about the current value of the process. So this is, let's say this is the current observation, right? So then the variance of that, this is what we're talking about here, okay, is a function of squares of its previous innovations, okay? So this is what you would basically have here, is a function of the squares, function of the squares of its previous innovations. Okay. So that's what we see basically in the equation. Okay? Again, so let me just illustrate this. Okay? So this is going to be the variance, okay? So you will see. I mean, to be precise, this is the variance of the process here, and it's a function of the squares, okay, of its previous innovations. Obviously, okay. I mean, the expectation, let's say, or the expectation here of that is a function, okay, of its previous innovations, okay, and this is captured, I mean, in time series in finance attempt to exhibit time-dependent volatility clustering. Okay, so this is very important here. So we have volatility clustering. Okay, so volatility clustering. So this is something that can be captured by the process. What does it mean? Now, what is the volatility now? The volatility is the standard deviation of asset returns. Okay, so that's the asset volatility. I know, I'm not sure whether or not you're familiar with this. Okay, so what does it mean? Okay, so volatility is the standard deviation of the returns of the asset. Okay, you know what returns are, right? The relative growth. Okay, so the relative, let's say, price changes, right? So these are the returns. So basically, this is, and then you take these relative changes and then you calculate the standard deviation of them. And the standard deviation of that will be basically the volatility of the asset, okay? All right? So the standard deviation of returns, okay? And what you would do is, I mean, what you observe in financial data basically is that you have periods of swings in the return of the asset followed by periods of relative calm, okay? So you have periods where you have high volatilities, okay? So let's say this is what you observe in practice, okay? So in practice you would have the periods, okay, with high volatilities, okay? Okay, and basically you would also have periods where the volatility is relatively low. Okay, so periods with relatively low volatilities. Okay, where basically the volatility comes down a little bit. Okay, depending on previous realizations. Okay. Okay, so that means that you have clusters. Okay, depending on time. Okay. And that can be captured by the process. Okay, so this is what it is for. Okay, I will show you some, basically next time I will show you some pictures related to this, so how you recognize, arch or arch effects regarding this. Okay, so arch effects can be basically captured. Okay, so these are the arch effects, let's say. This means that you have volatility clustering, so that means that you have periods where the volatility is high, okay, in a certain period of time, because the market is relatively nervous, okay, and if the market gets nervous, and everybody is nervous. Okay, so they have relatively large price changes in the market, and the volatilities are high. So that's what you can observe. And then of course you also have periods where everybody calms down a little bit. Okay, so no panic attacks whatsoever. Okay, so everybody calms down, and then of course the relative price changes of assets is also relatively low. Okay, so in that case you would have that the volatilities are low, and this this depends on time whatsoever. So this structure depends on time, and that can be captured because you have that here in this case. Okay, so look at this is what you have. Okay, so the current, let's say, volatility, the current variance, okay, of the process depends on the squares of the previous observation of the process, okay? All right, so this is something that can be captured here, okay? Now, I will discuss also some other additional properties that this process has, and this is going to be the first one, which is important here. Okay, so this is the first, let's say, proposition that we consider. Okay. And then, of course, let's say if, okay, so we have an autoregressive conditional heteroscedastic process for the Q, then basically you would have that the conditional variance of the process, okay, so the conditional variance of the process, okay, here, yt minus 2, sorry, I forgot, yt minus 1, yt minus 2, and so forth. It's going to be equal to sigma squared at point t. So you can see that basically that the conditional variance depends on time, although the unconditional variance might not be time dependent. Okay? Okay, so again, maybe you remember, okay, so the conditional variance depends on time. Okay. Depends on time, obviously. But basically you have that the variance of the process again, so the variance of the process equal to the expectation, okay, of sigma squared, and expectation of sigma squared does not necessarily depend on time. Okay, it can depend on time, but it does not necessarily depend on time. Okay, now let's have a look at that, because that is something which is important. So we'll see that's how it's going to be. Okay. All right. So how would you basically capture the conditional variance of the process? Okay. All right. Now, and let me just illustrate why this is, because that's important. Okay. And that's how you would basically